So let's take a look at an application that might help us better understand what these partial derivatives are doing for us. So what we have here is a model for temperature on a flat metal plate given by its location on the plate. So basically each point has its own xy coordinate, and this function describes the temperature at that particular location on the plate. So keep in mind here, so our temperature is measured in degrees Celsius, and our location, our x and y coordinates, are measurements in meters. And so what we're being asked to do here is to find and interpret the rate of change of the temperature with respect to distance. So that's going to be with respect to x in part A or y in part B, and we are focusing on the point 2, 1. So let's go ahead and take a look at this. So let's start with point A, or part A, I'm sorry. So in part A, we're looking for this rate of change of temperature with respect to distance in the y direction. So we're looking at the partial of temperature with respect to x. Now, the reason I prefer this notation is I know that temperature is measured in degrees Celsius, and I know that my lengths or my distances are measured in meters. So what I now know is that when I'm done with this process, the units that will be attached to this partial derivative will be degrees Celsius per meter. So let's go ahead and take a look at what this partial derivative might be. So this looks to me to resemble a quotient rule. I could use a power rule, but when it's like this, I find actually it pretty easy to use the quotient rule, because the partial of the numerator with respect to x is 0 times my denominator. And then the partial of my denominator with respect to x. With respect to x, the partial of 1 is 0. With respect to x, the partial of x squared is 2x. With respect to x, the partial of y squared is 0. So there's the partial of my denominator times my numerator. And that whole thing is over denominator squared. Now, this first term turns out to be 0. So that makes things much simpler. And so my numerator ends up being negative 120x over the quantity 1 plus x squared plus y squared squared. And again, my units are degrees Celsius per meter. And now they did specify a particular point. So my partial of temperature with respect to x at the point x is 2, y is 1. It's going to give me negative 120 times x over the quantity 1 plus x squared plus y squared squared. So it's going to give me negative 240 over 1, that's 4, that's 6 squared, so that's 36. That can simplify a little bit. 12 goes into both numerator and denominator. So I get negative 20 over 3 degrees Celsius per meter. And probably for what we're doing here, not the most friendly form, so I might write this as negative 6 2/3 degrees Celsius per meter. That's probably a little bit easier to understand in terms of change in temperature over distance. Okay, so what this says, or what this is trying to convey is this. So for a 1 meter movement in the x direction, at the point 2, 1, the temperature will do what? The temperature will drop or decrease 6 2/3 degrees Celsius. 6 2/3 degrees Celsius. And this drop would be in the positive x direction. So if I move 1 meter in the positive x direction, the temperature will drop or decrease 6 2/3 degrees Celsius. If I happen to move 1 meter in the negative x direction, at the point 2, 1, the temperature will actually rise. Will rise or increase 6 2/3 degrees Celsius. And that distinction is dealing with that negative. So I could have negative 6 2/3 degrees Celsius over 1 meter. So that's the positive 1 meter, or the 1 meter movement in the positive x direction. Or I could have 6 2/3 degrees Celsius over negative 1 meter. So this is where we have a 1 meter movement in the negative x direction, which would actually create a rise in temperature of 6 2/3 degrees Celsius. Now, this problem is really quite similar for part B, where we're looking at the rate of change of temperature in the y direction. Notice that when we go to find the partial derivative here of temperature with respect to the y direction, our units are not going to change. We'll have degrees Celsius over meters. My partial derivative is going to change just a little bit. Partial of the numerator with respect to y is still 0. When I do my partial derivative of my denominator, I still have a 0. The partial of the x squared term in the denominator will be 0, but I'll get a plus 2y from the y squared term. So plus 0 plus 2y. That's the partial derivative of the denominator. Then I need to multiply by my numerator, and then divide that whole thing by my denominator squared. So in this case, now we have negative 120y over 1 plus x squared plus y squared squared. And again, my units are degrees Celsius per meter. So if we go ahead and evaluate that at our point 2, 1, we'll get slightly different numbers. Let's see, we'll get negative 120 times 1 over 1 plus 2 squared plus 1 squared squared. So I'm going to get negative 120 over 36. 12 still goes into, or can be used to simplify numerator and denominator. If I divide them both by 12, I'll get negative 10 over 3 degrees Celsius per meter. And then thinking about a rate of change of temperature, mixed numbers probably a little easier to understand here. So we'd probably have negative 3 and 1/3 degrees Celsius per meter. So I can interpret this much the same way as I did above. So I could say, for example, that for a 1 meter movement in the positive y direction, in the positive y direction, what will happen to the temperature? The temperature will decrease. Temperature will decrease 3 1/3 degrees Celsius. And then for a 1 meter movement in the negative y direction, the temperature will increase 3 1/3 degrees Celsius.